And today's lesson is going to be about factoring special products. And so these special products are going to be a very specific type of example. They're not very common, but they are good to know. We're going to start by talking about what is known as the difference of two squares. And the difference of two squares looks like the following. We got an a squared minus a b squared. And that is going to factor into a plus b multiplied by a minus b. So if we threw some numbers in here, say x squared minus 9, all right, that can be broken down into x squared minus 3 squared, right, because 9 is 3 squared. And then that is going to be equal to, well, our a is going to be x, our b is going to be 3, and so this is going to be equal to x plus 3 multiplied by x minus 3. So pretty straightforward process. So why don't we do lots and lots of examples about that? So we're going to start here with example A. We're going to do x squared minus 25. The square root of 25 is indeed equal to 5. So we got x squared minus 5 squared. And then we're just going to plug that into the formula. X plus 5, x minus 5. Likewise, things can get a little bit more complicated on our a front. So we got 4z squared minus 1, which we can write as 2z quantity squared minus 1 squared, and that's going to equal 2z minus, I'm going to rewrite the 2 to make it a little less z-like, 2z minus, or plus 1, it doesn't matter if you put the plus or minus first, and then 2z minus 1. So that is a form of the difference of two squares. And you can actually use the difference of two squares to evaluate rather complex problems. So let's evaluate 54 squared minus 48 squared. And if you didn't have a calculator, right, and had to do this by hand, that would be rather difficult. Fortunately, we're all living with calculators today in our pockets. But we could rewrite this as the difference of two squares. We could say that's equal to 54 plus 48 multiplied by 54 minus 48. And while 54 plus 48 is equal to 102, 54 minus 48 is equal to 6. And then we just have to write out 102 multiplied by 6, which is equal to 612. All right, so there's not a ton of notes today, so I'm going to do a couple more practice problems of this type real quick, and then if you are watching this on the YouTube video, go ahead and skip forward till you see the perfect square trinomial. But until then, let's go ahead and continue working on the difference of two squares. So we're going to do a whole slew of problems. So number 1 is going to be x squared minus 36. Number 2 is going to be 100 minus m squared. Number 3 is going to be 9n squared minus 16. And number 4 is going to be 16x squared minus 64. All right, so let's go through each one of those. We can rewrite x squared minus 36 squared as x squared. The square root of 36 is going to be 6 squared. And so that's going to be x plus 6 and x minus 6. And now take a minute, look at the next three, look at what you think they're going to be. You can divide 100, take the square root of that, and that's going to be 10 squared minus m squared, or 10 minus m and 10 plus m. You're going to have to take the square root of both of these, so that's going to be 3n squared minus 4 squared, and so that's going to be 3n minus 4 and 3n plus 4. Like I said, it doesn't matter the order you put the minus and the plus, that's just trivial. And then we're going to take the square root of both of these, so that's going to be 4x quantity squared minus 8 squared. Notice here that you can factor out a quantity of 4 from both of these, so we're going to take 4, factor that out, that's going to be x squared minus and so now we have to be a little careful here. So let's back up. Let's factor our 4 out here from the beginning. So we're going to factor out that quantity 4 from the beginning, and that's going to be 4x squared minus 16. And now we can go ahead and write this as a product of two squares. So that's going to be 4 times 2x squared minus 4 squared. And so that's going to be equal to 4 times 2x plus 4 multiplied by 2x minus 4. All right, so I'm only going to do 4 of those types of problems. If you'd like to see more, please let me know. If not, let's move on to the perfect square trinomial. And so there's a couple of different ways these can be written. You could have a squared plus 2ab plus b squared. So if you see something of that form, that is going to be written as a plus b squared. Or you can have a squared minus 2ab plus b squared, and that's going to be broken down into a minus b squared. So an example of each one of those, if you see something that looks like x squared plus 6x plus 9, that can be rewritten as x squared plus 2 times x times 3 plus 3 squared, which is going to be equal to x plus 3 squared. So the thing you're going to be looking for is if the first part of this is a square and the second part is a square, and then the middle is 2 times the first square x and the second square 3. Right? A different example here, we could have something like x squared minus 6x plus 9. All right, the square root can be written as x squared minus 2x times 3 plus 3 squared, and that's going to be broken down into x minus 3 squared. And so we can have some factoring of that as well. So let's factor something like n squared plus 8n plus 16. Yes, Jazz, we got some algebra today. Sorry I missed your comment earlier. Let's break this down. The square root of 16 is going to be equal to a 4, and then if we divide 8 by 2, notice that's 2 times by 4, right? And then we have this hidden 1 out there, so we can add that 1 right there. So this can be rewritten as n squared plus 2 times n times 4 plus 4 squared. So we are in this top category. And so that would be equal to n plus 4 squared. A different example, one a little more complex, we can do something like, so we're going to factor, we could do something like 4x squared minus 12x plus 9. All right, notice that this can be rewritten if we take the square root of that as a 2, and the square root of this as a 3, and then 2 times 2 is 4 times a 3 is indeed equal to 12. So let's rewrite that as 2x quantity squared minus 2 times x times 3, and then plus 3 squared, which is going to be rewritten as 2x plus 3, oops, sorry, 2x minus 3 squared. Notice that if you have a negative here, then you will result in a negative there. And if you have a positive here in the second position, then you're going to have a positive here. So that's the difference between the positive and the negative. All right, why don't we go ahead and try a very complex problem, something like this. X squared plus 2/3 x plus 1/9 is equal to 0, and I want to solve for x. So these fractions are really scary, but notice that each one of these fractions can be multiplied by 9 to get a whole number. So why don't we multiply this entire formula, both sides, by 9? And when we multiply 0 by 9, that's still going to be 0. So we're going to have this as 9x squared. 2/3 of 9 is going to be 6x, and 1/9 of 9 is going to be 1. And then 0 times 9 is equal to 0. Notice then we can take the square root of 9x squared and get a 3x, and get a square root here and get a 1, and then 2 multiplied by 3x times a 1 is equal to 6x. So this can be rewritten as 3x quantity squared plus 2 times 3x times by a 1 plus a 1 is equal to 0, or 3x plus 1 squared is equal to 0. Take the square root now of both sides, and we're going to get 3x plus 1 is equal to 0. 3x is equal to a negative 1. X is equal to a negative 1/3. I know that example might have been a little complicated, so why don't we do another one similar to that, this time without the fractions. So let's solve for x on m squared minus 2m plus 1 is equal to 0. Let's factor this left-hand side. So notice that the square root of m is an m, square root of 1 is a 1, 2 times 1 times m is equal to that. So we're going to write this as m squared minus 2 times m times a 1 is equal to, oops, not equal to, plus a 1 is equal to 0. We can factor that down into m plus 1 squared is equal to 0. Take the square root of both sides to get m plus 1 is equal to 0. Subtract the 1, m is equal to a negative 1. And another problem, we're going to do n squared minus 81 is equal to 0. This is not in the formula that we've been working in, but back up here to the difference of two squares. Notice that we can rewrite n squared minus 81 as n squared minus 9 squared is equal to 0. So that's going to be n plus 9 multiplied by n minus 9 is equal to 0. And now we have to set up two different formulas. N plus 9 could be equal to 0, or n minus 9 could be equal to 0. Subtracting 9 on both sides gives us n is equal to a negative 9. Adding 9 on both sides, we get n is equal to a positive 9. All right, and just because I've gotten some requests to do some extra problems, that's all we're doing today. So if that's all you need, you can leave. If you want to see some extra problems, I'm going to do those now. So why don't we take a look at something like d squared minus 10d plus 25, right? This can be rewritten as the square root of d is d, the square root of 25 is 5, and then 2 multiplied by d multiplied by 5 is indeed 10d. So that's going to be d squared minus 2d times a 5 plus 5 squared. We can rewrite that now as d plus 5 squared. Let's do one last one. So we're going to do 9z squared plus 36z plus 36. The square root of 9z squared is going to be 9z. The square root of 36 is 6. 2 times 9z times 6. That doesn't add up, does it? Let's change the middle here to make that add up. 2 times 6 is 12. 12 times 9 is 108. Z, I think the guy that wrote down the problem made a mistake here, which would have been me. Anyways, we can rewrite this now as 9z quantity squared. Actually, I made the mistake, not the textbook. The square root of 9z squared is 3z. And now 2 times 3 is 6. 6 times 6 is 36. So now we can rewrite this as 3z quantity squared plus 2 times 3z times 6 plus 6 squared, or 3z plus 6 squared. Once again, minus there needs to be a minus here. It's really easy to make those simple mistakes. And a plus here means a plus here.